Thank you very much, Holger, and thank you very much, Kevin, for organizing the seminar, and you all for being here. Yes, I'm presenting this rather new old technique, and before starting, I would like to give you my outline for the talk. So I will start with a brief introduction of myself and our laboratory. Now I'll go into the details of a spatial atomic layer deposition, and I will finish up with some examples of applications of this remarkable technique to new generation photovoltaics. So I don't need to repeat that. It's pretty much what Holger was telling, and these are all the research topics I've been working throughout the years, and we can sum up this and summarize as having extensive experience in the preparation of characterization of novel materials, in particular new silver copper oxide phases and hybrid nanostructures, and applying them mainly for energy-related applications such as photovoltaics on energy storage, mainly lithium batteries and supercapacitors. And currently, I'm also involved in work related to transparent conductive materials. So I'd like to take the opportunity to advertise this book that has come out fresh from the print and that I have co-edited with Xavier Moya from the University of Cambridge, that covers from conversion to utilization of materials for energy, and I think it's quite interesting. And I like to make a point of the chemical approach I've always used, and using always techniques that are low cost, scalable, and that can be used industrially. So this is a kind of the picture of myself, of my research. And today I will be talking mostly of this spatial ALD approach and CVD approach, and also transparent conductive materials that we are developing in the lab. So where do I work? It's in France. This is Europe. France is here. I come from Barcelona, here in Spain, so not too far away from home. Grenoble is here, very well located, close to Switzerland, Italy, Germany, Spain. And in particular, Grenoble is situated here, and it's quite remarkable because it has this kind of Y shape, and it's surrounded by three chains of mountains, La Belle d'One, Chartreuse, and Vercors. So it's a remarkable, nice environment. And one of the PhD students in the lab, well, just went in the morning before going to work for a hike and managed to take this nice picture where you see the different mountains surrounding Grenoble. And you can spot here the Mont Blanc. So if you like hiking, the mountain sport is a very nice place to work. Our lab would be located here. If we go more into the detail, this is again the map of Grenoble, and it's a very nice environment to do science because we have two campuses, two scientific campuses, the old one, where most laboratories were and are at the beginning, and this is the new campus where some old facilities as the neutrons and synchrotron are placed, but new labs as we have a huge biotechnology lab, and we have also a nanotechnology institute with a nanofabrication lab similar to the one you have here. So it's very convenient to do material science and devices and different applications. And as you can see, we have many, many students, and in Grenoble, 20% of the people is involved in research and science, so it's quite a rich scientific environment. The first university was created by Joseph Fourier in 1810 in the old part of Grenoble, so yeah, again, a nice place to work in. And going in particular to our laboratory, the Laboratory of Materials and Physical Engineering, is a mixed laboratory between the Grenoble IMP, it's a school, Polytechnic University, and the National Research Center in France. And we're mainly organized in three groups, one dealing with crystal growth and high temperatures, working with silicon carbide and this type of semiconducting phases, max phases, and 2D materials, and focusing mostly on the thermodynamics of this growth, high temperature growth. Then we have another group dealing with the interface between materials and biological matter, mostly biotechnology. And finally, this is the group, thin films, nanomaterial, and nanostructure, to which me and my student Viet, who is here, belong. And mainly here, well, in the three cases, we apply chemical approaches, mostly. We don't do any physical deposition method. And we try in this group to optimize the growth of building blocks for different type of applications. So we spend a lot of time trying to understand how we grow the materials and the properties and the morphology and the structure. So it is organized in four research axes. The first one is dealing, as I say, with the deposition and characterization and understanding of these building blocks, nanobuilding blocks, by these chemical approaches. Then we have another groups working on in situ characterization, for instance, with instruments that we ourselves develop, transparent conductive materials, and wet surface chemistry and surface functionalization. What I will be talking about today would be inside those two axes here. So far as for the lab and myself, I will move now fast into the new technique that I'm going to present. But before doing that, I would like to start with an example, because what I'm presenting here is a new processing technology. So the chemistry is known, and the technique, the basics of the technique is basically something known. The interesting thing is the way we process it, we do it. And sometimes it's hard to combine people. The way you process materials is also very important, apart from the properties of the material. So if we look at the case of aluminum, for example, and we compare it with gold, nowadays, gold, of course, is very valuable. It's very expensive, so nobody would think about doing a plane of gold. Maybe some of these very rich people that is helping you so much could afford it. But of course, most of us will look at it as an extravagance. On the other hand, aluminum, we all know, is very convenient, it's very cheap, so we can even use it to wrap our food. But it has, apart from being cheap, very nice properties, because it's allowed us to fly in only 60 years to go from the sky to the moon. So it's a remarkable material, but it was not always like that. Napoleon used to impress his guests by offering the dinners with aluminum cutlery, because at that time aluminum was very expensive. And it's hard to understand, because if you look at the abundance of elements from the periodic table, you see that on Earth's crust, aluminum is the third most abundant material, so it should be quite cheap. The problem is that it's very reactive, so you mostly find it associated to oxygen in the bauxite ores, and it's quite not so straightforward to reduce it and obtain it as a metal. And it was not until electrolysis was discovered, and we managed to control electricity and to do chemistry with it, that we managed to reduce aluminum by melting it and then reducing the aluminum. And that was something that was found by Friedrich Wöhler, an organic chemist, quite remarkable. You see, of course, he's very remarkable. That's why he also deserves an stamp, like Napoleon. And in this case, he's not remembered by discovering how to reduce aluminum, it's mostly by synthesizing urea. And that's quite remarkable, because it was the first compound present in living organisms that was synthesized in the laboratory, and was quite an impact in the time, because of course living creatures were meant to be made by God only, so that was quite of an earthquake at the time. But also this French guy, Saint-Clair Deville, 10 years later also discovered how to produce aluminum independently, and he's also well remembered. But then even with this process, it would be still not viable to produce it this way. So it was until, again, Paul Hérault and Charles Hall in the United States discovered that you could dissolve aluminum oxide in cryolite, with sodium and fluorine, and then you could reduce the temperature of the process to below 1,000 degrees, and that made the process viable, economically viable, and as important as it is today. So unfortunately, apparently for the United States, that's not such a remarkable thing, and I couldn't find a stamp for Charles Hall, unfortunately. But the funny thing here, if we look at the biography of these two researchers, and as many other examples in science, if you look, they were both born at the same time, the same year. They managed to find the same trick to produce aluminum in a cheap way the same year when they filed the patent. And unfortunately, they both died quite young, the same year as well, because they were poisoned by the fluorine gas that was delivered during the reaction. So quite a nice coincidence. And of course, the process is so important that it also deserves a stamp, at least. So going to Spatial ALD in particular, and again, to show how important it is to find new ways of processing materials, Spatial ALD, and in particular ALD, is we need to compare it with chemical vapor deposition, because it's very similar. But the difference is that the chemical vapor deposition, which has been known and used for more years, you inject different precursors in a reactor, and then they will react in a substrate which is thermally activated. It's heated, so that the reaction is thermally activated, and then the byproducts are eliminated, leaving you with the film. But you can do that, but you can also do a sequential exposure of your substrate to the precursors, and that's why what transforms CVD into atomic layer deposition. It's basically very similar, but in this case, you first expose your substrate to the first precursor, and you give it enough time to saturate the surface. When all the surface has reacted, you have your monolayer form. The excess precursor is purged, and then only when everything is clean, you inject the second precursor that can only react with the first monolayer. And again, you wait for it to react completely, and any excess is purged. By doing the reaction in this way, you get unique properties. The first one is that the thickness is very precisely controlled, because it only depends on the number of times you repeat this cycle. You get growth per cycle, which is a particular one for each reaction and reactor, but once you know it, you can repeat it as many times as you need to get a particular thickness. The other unique property is that the only technique that allows a uniform and nice quality film over high aspect ratio features, because the precursors have enough time to diffuse and to react with all the surface. And then you can see that the film is homogeneous, the thickness is constant, and the same is valid for large area surfaces. It's the only technique that can give you a very homogeneous film. And the third quality is that the films that you obtain are quite high quality, even at low temperatures. And this is due to the chemistry which is behind, and it's due to the precursors being used, which are, in this case, very reactive. If you compare ALD precursor with a CVD precursor, you can see that the CVD precursor is quite stable. You can handle it in the open air, while ALD precursors are more reactive. In this case, it's the ethyl zinc, a typical precursor for growing zinc oxide, which is pyrophoric, which will catch fire the moment it sees the air or water. And you see here, if you compare the properties required for a good CVD precursor, and you check those for an ALD precursor, they are basically the same, but in addition, for ALD, you need to have a very reactive precursor, but with high thermal stability, because you don't want it to decompose before it reaches the surface and reacts with an active site. So, due to these unique properties, this is a technique that has become very popular. It is now pretty much in every lab, and the labs that don't have it are in the process of buying one or making one. And there's been a lot of papers and reviews dedicated to the technique. It's very widely used now in the laboratory, especially with the coming of nanoscience and nanotechnology. It's become very useful because it allows you to nano-engineer the surface and in the interfaces, which is very important for devices as well. But nevertheless, it has two main drawbacks which have prevented it to being widely applied in industry. The first one being that it's very slow, because of course you have this sequential injection and purge of precursors. And the second is this mostly processed in vacuum, and that makes the scaling up quite more complicated and expensive. So which would be the solutions for that, so that we can use it even in industry? Well, the solution is to go from this. This is the scheme of conventional ALD that I have been explaining, in which you inject the precursor, you purge, you inject the second, and the sample stays still in the reactor. What you can do is inject the precursors continuously in separate locations, kept away by an inner gas flow, and it is the sample that goes from one to the other. As it does so, it replicates the conventional ALD cycles because it goes through this inner gas zone, and that cleans the surface. Funny enough, both approaches were already published in 1977 by Suntola in Finland. And if you see at the figures and the reactors he proposed in his original ALD patent, you can see that the first three designs he proposes are the spatial ALD reactors, where you have two precursor bottles and you have a rotating substrate holder exposing the samples to the different precursors with a vacuum pump to eliminate any unreacted precursor. And then only the fourth design corresponds to a temporal reactor in which you sequentially inject the two different precursors. He then developed it a bit further, and in 1983, he realized that he could do that without using vacuum, by using a gas flow, which could keep apart the two precursors. And then by doing it in this way, you can come up with systems in which you can do this processing at atmospheric pressure even. So it's quite remarkable. And despite that, and despite the date, pretty much everybody and all the commercial ALD was done in this temporal configuration under vacuum. So it was only, before, to see more the analogy between the different approaches, you see immediately that in this case it's much faster. You have gain in speed because the precursors are all the time there, and then you don't need to purge. You eliminate this long step in the middle, so you can go much faster. And because you are using gas flows to separate the precursors, you can operate at ambient pressure, as I say. So if we find an analogy, you will see that temporal ALD would be like a normal restaurant where you need to wait for the waiter to get the menu, then to wait for the waiter to bring the first course, and so on and so forth. If you compare it with a buffet in which you have all the precursors ready. You just need to go and take what you need. So it's going to be much faster to produce this reaction. And I should point out that our Spatial ALD is high quality ALD, not bad quality. But then, as you've seen, the patent is from 1883. And it was just in 2004 that the first paper I found was published on this spatial approach. Before that, it was pretty much temporal ALD. And here you can see, again, we have one precursor, oxygen, to oxidize it, and a substrate that is moved from one region to the other, blown by an inert gas flow. As I say, this is the first paper on spatial ALD, and it's a shame because traditionally it's not the one that has been cited. You will see that it's another one by Kodak 4 years later. And I say it's a shame because they published it first, and not once, but twice. They managed to publish the same thing, Spatial ALD approach for the formation of hafnium oxide, with the same properties and pretty much the same day in 2 different journals. So it's quite remarkable, but unluckily they are not cited. So the first paper that is normally cited and that uses the approach hinted by Suntola in his patent was Kodak, in which they synthesized stable zinc oxide thin film transistors using this technique. So the thin film zinc oxide was grown in the atmospheric pressure. And then this year, the second paper came, and it was between Kodak and the University of Cambridge. They were working together. And then Kodak decided to close the research center in Europe, and the department, with Professor Driscoll's group, got the reactors they had developed. And that's how myself and Kevin Musselman we started developing this technique, because we were at that time postdoc, myself, and he was a PhD student, and we started optimizing this novel approach for application in new generation photovoltaics. You see that the approach is very versatile and can be implemented in many different engineering approaches. This could be the original approach patented by Kodak, which is very similar to what had been proposed by Suntola. And essentially, you just have a head in which the different precursors are separated and distributed along parallel channels. But you can do the same by having different regions and going from one to the other across an inner gas, or by having this tubular flow, or even for powders, you can have a tubular reactor in which different regions are exposed to different precursors and inner gases. So it's quite versatile. It is growing slowly, but at a constant pace. And we have now many groups developing it. We have even commercial systems. We have these 5 commercial systems. These 2 are dedicated to production, and those 3 are more for the laboratory scale. And you can see that we have many groups already developing this approach with homemade systems. And University of Waterloo here starting to develop it with Professor Musselman. And we are the ones in France doing it in the laboratory, and also a spin-off company from Paris. So this is schematically how a Spatial ALD reactor works. We have bubblers containing different precursors, which should be volatile, and then we flow nitrogen through the precursors, which carries the vapor of the precursor to the manifold head. And there is where we manage to separate them along parallel channels. And then by getting the substrate very close to the head, at 150 microns, we manage to prevent mixing from the different precursors, and then we just need to scan this substrate back and forth to replicate the conventional ALD cycles. In here, the sample would be exposed to the metal precursor, then it would be swept by this nitrogen flow, and then, again, it would react with the oxygen flow. So you can see that we can do it very easily. And here, for instance, is just to illustrate how much fast it can be. If we compare Spatial ALD, this approach, with conventional ALD, here we can see that every time we are scanning back and forth, we do 4 conventional ALD cycles. And by the time we've done 12 here, we are still at half cycle here. We just saturated the surface with a metal precursor. And of course, this is just an approximation. That this is the order of magnitude of difference. A Spatial ALD can be up to 2 orders of magnitude faster than conventional ALD. So it's quite interesting. This is some of the examples, the samples we used to deposit at that time in Cambridge, where we started developing this equipment from Kodak. And this is TiO2 deposited at 250, already crystalline, very homogeneous, over centimeter scale. This is 6 centimeters by 6 centimeters. Again, because we can do it at low temperature, we can use plastics as substrates. And the good thing about this close proximity approach, as it is called, because as I say, we need to have the substrate close to the head, is that we can switch between more ALD, strict ALD conditions, but also CVD, because we can tune the flow through the metallic or through the precursor channels, and we can play with the gap, and we increase the precursor flow, and we get a bit away from the substrate. We allow certain mixing of the precursors, and then we're going to have some CVD growth. On the other hand, if we get closer and we increase the nitrogen flow, we are favoring more strict ALD, so only surface-limited reaction. And that's an advantage because for surfaces like this, for this kind of substrates where you don't have any feature, complicated feature, high aspect ratio, you don't care whether you're actually doing CVD or ALD as long as your film is uniform, dense, crack-free, no pinholes, and you manage to go much faster because you go from ALD to CVD, so you are speeding the reaction a lot. And we wanted to try these two approximations on nanostructures to see also how conformal the deposition would be, because ALD is supposed to be conformal. And in this case, we tried to coat zinc oxide nanorods, which were electrodeposited, with a thin layer of aluminum oxide. And you can see here, using the ALD conditions, we did 20 cycles at 2 millimeters per second. That's the scan speed. And of course, it took 12 minutes because we were doing it slow to give time for the surface to saturate. But you can see, or maybe you cannot see, but believe me, you have here 5 nanometers of aluminum oxide, which is conformal only on the nanowires. We did, of course, twice the number of cycles to confirm that we get a thicker film. And you can see here, this is still very nice, conformal, homogeneous. But of course, it took 25 minutes, so not that fast. Then we say, let's go to CVD, see what happened. And in this case, we modified the conditions to be more in the CVD-like mode, and we did 60, so still 20 cycles more, but much faster, only 3.5 minutes. And you can see that still the film is conformal. The thickness is proportional to the number of cycles, so because the surface of the nanorods is, after all, more active, you still coat them. And it's dense, crack-free, very nice. So you can use Spatial ALD even in CVD mode to coat nanostructure with relatively high aspect ratio. This is the system we have developed now in the laboratory in France after I got there, and it's very similar to the approach followed by Kodak. So the main piece is the head, where we managed to distribute the different flows in parallel channels, and the rest is just the gas panel, the electric control, the valves, but it all happens here. You have the sample in the substrate, which is going to scan back and forth, and we have the head distributed, and we just try to make a better adjustment of head and substrate because it's very important to have a parallel alignment, to have a very controlled gap distance so that you will be homogeneous and you will be reproducible. So that's what we are working on. And also we are trying to play with the head design and the gas panel to be able to do complicated structures like multi-layer structure and complex oxides by managing to selectively inject precursors at different moments in different locations. And that's the team in the LMGP which is contributing to this work. This is the first PhD student in the laboratory working on that. He's sitting there, so you will be able to talk to him if you want to have more details. And that's a video where you show how we actually grow a film. Time 0, we start silating the sample under the head. We're growing zinc oxide, and you will see that just after 20 seconds, hopefully you manage to see, we have already a film appearing there. You see that we are really close to the substrate to ensure that the gases are kept apart from each other. After a little over a minute, you see the film, which say is 30 nanometers, maybe 40. Keeps growing. We are at 2 minutes. You see it's much thicker now. And you will see that after 3 minutes, it's very thick. You can see difference in color. It's homogeneous. It's around 100 nanometers. You can see how nice and bluish it comes. So it's really convenient. Once the sample is adjusted, everything is adjusted, saturated, you can see that you can grow a lot of samples in a short time. So it's very convenient. And it's one of the main advantages. Then you have many other advantages, as the possibility of printing oxides like that in ALD mode, CVD mode, but it's large scale, fast deposition technique, so it's very, very convenient. So after showing it to you, I will give you some examples of application. In this field of photovoltaics, I will make first couple of examples of application of active component for new generation solar cells, and then I will quickly describe some of the work we're doing in the lab concerning transparent conductive materials, and some of the applications we have done already of this AP SCALD new equipment to this field of research. More of what we did was summarized a couple of years ago in this review in Materials Horizon, so you are invited to check on it if you want more details. The first example concerns bulk heterojunction solar cells, and we chose these cells because those cells are, as the name, well, not the name, but they are done with organic semiconductors. Organic semiconductors are good because they can be processed at a low temperature from liquids, so they can be done on plastic substrates. And they just replicate a conventional inorganic diode where you have a donor and acceptor, and then one of them or both can absorb light, and the photogenerated electron can be injected, and then you close the circuit, you have a solar cell. But as I say, you can process them at low temperature and from liquid. The key thing here is that because the diffusion length of charges in these materials is much shorter than in inorganic semiconductors, so you need to kind of form this bulk junction between them to ensure that once the charges separate, you want to split the exciton, as it's called, this boon electron hole pair, the charges are able to reach the electrodes. And for those of you not familiar with photovoltaics, the way we characterize the solar cell, the basic way of characterizing it is to do an IV curve. Then you want, under the dark, to have a really nice diode, which will rectify. And then when you illuminate it, you want to generate a certain photocurrent as much as possible with a certain open circuit voltage as much as possible as well. And you want your diode to be as perfect as possible, and that's what this fill factor is giving you, how perfect your diode is. And the more square it is, the more power you can get from the cell for the same open circuit voltage and short circuit density, current density. So again, we wanted to apply a special atomic layer deposition to this system because, as I say, it's a system that is processed in liquid, roll-to-roll, fast, high throughput processing, low temperature. So if you want to make some of the components in a compatible way, you need to have a good processing method. In this case, what we wanted to do is this interfacial layer. As I said, you have a bulk heterojunction layer here in which charges can reach both electrodes. So in order to prevent recombination in the electrode, you need to make these electrodes more selective so that only electrons or hole will be allowed to reach the contacts. And we do that by depositing oxide layers that should be, of course, compact, homogeneous, as thin as possible, and transparent. So we decided to apply a TiO2 layer on this type of cells, and the A here stands for atmospheric ALD because at the time we still called it like that. And we see we deposited a very thin layer of TiO2 on top of this bulk heterojunction. We did another one at 350, this was at 100, and then we compare with a layer made by a spray pyrolysis at 450, which we knew it was good, compact, and would perform nicely. So when we compare the results, you can see that cells fabricated with the 3 layers perform the same way. So ALD is as good as spatial ALD as spray pyrolysis. And you can see here the thin layer of TiO2 made at 100. But the good thing here is you compare how long it takes to deposit this layer comparing with other processing methods done on low temperature and ambient pressure. You can see that the spatial ALD is 2 orders of magnitude faster. So this is quite remarkable. This technology is high throughput fabrication, so you need something capable of matching this speed. And the other thing that has to be noted here is that if you look at here, we have a 15 nanometer layer of TiO2, which is amorphous, so conductivity should be awful. And we're still able to do a solar cell which doesn't have a huge series resistance because we're using a thin layer. And we're able to use a thin layer because the layer is perfect. It's crack-free over centimeter scale again. So this technique allows to use a very amorphous, low temperature growth layer, very thin, which is still able to perform really well. So it's quite remarkable. Another example was this system, copper oxide, zinc oxide solar cells. And this system is interesting because if you look in this paper, an analysis that was made on different materials that could be good alternatives to silicon photovoltaics, which is the current technology, the ones here were the most interesting because they can be produced in a cheaper way. than crystalline silicon, and they have the potential to deliver more current, of course, if they do it at the theoretical efficiencies. And if you have a quick look at this graph, you can see that one element is quite remarkable. It's copper, and we have different phases in which copper is present. So at that time in the group, Kevin Musselman was interested in the system, and he was trying to make with copper oxide, cuprous oxide, zinc oxide solar cells by electrochemical deposition. So we decided it would be interesting to study this system and to complement it with Cu2O oxide grown by Spatial ALD technique. You see that many research is devoted to this system, so we are still quite far from 20% theoretical efficiency, but we're doing our best. And the problem with this system is that we have here an incompatibility between absorption length, the amount of materials you need to collect most of the light, the amount of material you need to have a full depletion layer, and I won't go into the details because I don't have enough time, and the thickness you can have to ensure efficient charge collection. And that limits quite badly the efficiency you can get. So what we did, as I say, and that's a very nice paper that Kevin published at the time, where we used zinc oxide nanorods to try to maximize this charge extraction. It was even featured in the cover. What we tried to do, as I say, was to grow this material with atomic layer deposition, spatial atomic layer deposition approach, to see whether we could improve the efficiency of the system and the properties of the cell. And then we optimized this deposition using this cuproselect precursor, which is a copper +1 commercial precursor, and reacting it with water. We managed to establish the temperature window of stability below 300 degrees. And basically, we can see that for two different growth conditions, we got different growth per cycle, but it's still proportional. So we are still in ALD-like conditions, even if it's a bit of CVD. But you can see that depending on the number of cycles, we got a particular thickness. And again, we tried to coat nanorods with our spatial atomic layer deposition system. And you can see, again, it's very conformal, very neatly coated. And again, you can deposit on different substrates, metal, plastic, because we could do it even at 125 degrees. And again, the films are nice, homogeneous, crack-free, quite smooth. So very nice. When we checked the structure, it was pure cuprous oxide to the TM, no metallic copper, no copper oxide. And the only difference is by increasing the deposition temperature, the grain size was increasing, which led to a decrease in resistivity because, of course, mobility increased with the deposition temperature. And if we look at this mobility obtained at 225, it's quite remarkable because you can compare it with the mobility obtained for films deposited by electrodeposition, and it's quite low. And it's comparable to mobilities obtained for cuprous oxide films obtained by thermal oxidation at 400 degrees. So we're still almost 200 degrees lower in temperature, and we managed to get high mobility and relatively high carrier concentrations as well. You will see that this is 10 to the 16. And we try to take advantage of this value because the electrodeposited copper oxide that Kevin was using and other members of the group had a carrier concentration of 10 to the 13. So what we did, we tried to fabricate a more complex cell in which we deposited a layer cuprous oxide by SLD on top of the previously electrodeposited copper oxide in what is called a back surface field cell. And the objective here is to dope some of the holes of the SALD layer into the electrochemically deposited layer. You can see here the cell with the SALD layer. And if you see here the different efficiency for the different cells, you can see that the one in which we deposited this layer of a spatial atomic layer deposition cuprous oxide, we managed to increase a great deal the short circuit current. And at the time was the highest reported for this type of system fabricated at ambient atmosphere and for chemical methods. You can see also that we managed to reduce the amount of cuprous oxide that you need to have to get this order of this efficiency from 3 microns to 1 micron. So again, I won't go into the details of the physics of this device because it's quite complex and I don't have the time, but just a rapid example of how we could use our special atomic layer deposition system to improve the performance of our devices. And without going into the details, these are other quick examples in which we show that not only we can deposit simple binary oxides, we can also dope them. And by doping them, we can peer and probe the device physics and understand more complex hybrid systems and phenomena. So those are quite nice examples of how by doing this doping, which is quite easy to do, we can get a deeper understanding of the different solar cells that we were studying. And again, speed is important at the industrial scale, but at the laboratory scale it's also an issue because all this work that we were able to do would have been impossible with a conventional ALD system because it just takes too much, it's too long, it's harder to modify, to optimize. So having this system that we could tune allowed us to do all these studies. So we'll finally move to these TCM studies that we are doing now in the laboratory, and we have different axes. We work on TCOs, oxides, and we work on TCMs using silver nanowires. And as you all know, TCMs are used in many different applications, are now part of our everyday life. And of course, ideally you want to get a material that is as transparent as possible and as conductive as possible. And this is quite hard because both properties go against each other. So yeah, there have been different solutions that have been found so far. The most traditional one is the TCO approach, these families of oxides which are transparent and still quite conductive. And the main one is indium tin oxide. But of course it contains tin, so it's rather expensive. Tin is not abundant, so it can imply a problem for widespread use. And also these type of materials are brittle, so for flexible applications, there's also alternative materials such as graphene, carbon nanotubes, or metallic nanowires networks. So as I say, we're focusing in the lab in FTO, aluminum doped zinc oxide, and transparent conductive materials based on silver nanowires. And in the first example, again, we're trying to take advantage of the properties of a spatial atomic layer deposition to enhance the performance of a device. In this case, the system is bulk junction solar cells. And this type of cells is very similar to a crystalline silicon solar cell. But what we do is we have the crystalline core, and we passivate it with a thin layer of amorphous silicon, which is doped P and N on each side. And this layer passivates the surface of the silicon, which is not in contact with the electrodes, and that prevents a lot of recombination. So the efficiencies achieved are very high, much higher than for conventional crystalline silicon. But the problem is that these layers of amorphous silicon are not conductive enough, so you still need to have a TCO layer on top of them to collect the charges. The problem is that you want to deposit this layer of TCO at low temperature, because if you process it at higher than 200 degrees, you are going to crystallize the amorphous layer, and you are going to lose your enhancement. So we have a project with Ines in France, in which we are trying to develop these aluminum doped zinc oxide layers for this type of solar cells. And it's an example of the zinc oxide we are currently optimizing depositing. And again, when we try to deposit it on top of a textured silicon substrate, you can see that it's really conformal and nice. And that's the PhD subject of Viet. And I have it twice, so here we go. So the first results, we're still optimizing the layers, the properties, the electrical properties and optical properties of the layer, but already from the passivation point of view, we see that after depositing the amorphous silicon layer, we have a good open circuit voltage. But after depositing the zinc oxide layer with our spatial ALD, we even improve it. So we are not even, not only not spoiling the efficiency of the cell, but even improving it a bit. So it's promising, and that's much of what Viet is currently doing in the laboratory. In the other project, it deals with the silver nanowires-based transparent conductive material. And here, what we do mostly is physical studies. I collaborate with Professor Daniel Bellet, who is the leader of this research axis. And we get these silver nanowires with this pentagonal shape commercially. We purchase them, we deposit them, And then we try to measure the properties to optimize it, to model the behavior, and then to understand what happens between this stage of no percolating network to this percolating regime where you have current flow, and what happens beyond that. And the way we do it, as I say, we deposit the nanowires, and then after depositing them, we need to do a heat treatment to enhance the junctions between the wires. And once we reach an optimum temperature, the resistivity is optimized. And if you continue heating, you're going to have this Rayleigh instability, and your wires are going to spheroidize. So that's bad, because one of the applications of this type of TCNs is as transparent heaters to defrost the screens of motorbike helmets or for the planes, windshields. And you can see here, for instance, if you apply a voltage to your network to try to increase the temperature, you can see that the resistance you get as a result of the increase in temperature is not constant. It is evolving, and the higher the voltage, the faster is this increase in resistance, which means that your network is not stable. You should reach a resistance value for a particular voltage that should stay still, which would mean that you get a stable network, which is not the case. So what we're trying to do, and is to protect these networks with a thin layer of oxide to try to enhance its stability to thermal and electrical annealing. You can see here we made a thicker coating just to be able to image it, but normally we work with 6, 7 nanometers. In this case, it's around 30. And you can see that, again, the coating is really conformal, homogeneous, very nice. And this is research work that is done in collaboration with Dr. Guyen in Liège, and mainly done by Sarah at Agatha de Horts. I hope I say it right. And then you can see that, yeah, after applying this oxide coating, you can see that the potential becomes much more stable. And in this case, for instance, when we reach 7 volts, if the nanowires are not protected, the network fails, start failing. And when you go back to 5 volts, the voltage is much higher than it should be. While when you have them coated with zinc oxide, you recover pretty much the same, even lower resistance, because the junctions have been improved, so you have less resistance, and the whole device is stable. This is another example where you have, again, the nanowires coated by the zinc oxide, and again, very conformal. And here is the same. As you increase the voltage, if you don't have protected wires, they will become spheroidized, and your network will be lost, and therefore the resistance becomes infinite. And as you increase the thickness of the coating layer, you manage to increase the amount of the temperature and the voltage that you can apply to your networks. So that's another thing in which we are working. So going to the conclusions, I hope I have convinced you that spatial atomic layer deposition, or atmospheric pressure atomic layer deposition, is not so novel because it was patented a long time ago, but it's recently been developed. And it's just a variation of conventional ALD, where precursors separated in space and not in time and kept away by an inner gas flow. It in principle has the same advantages than conventional ALD, but much faster, compatible with roll-to-roll processing and other printing methods, cheaper and quite easy to engineer and scale up. And as you've seen, it allows fundamental studies, not just printing an oxide, but you can dope it, you can study the physics of different devices. So it's quite convenient, and of course we're using it to do high-quality oxide films as passive and active component in different devices. So I don't know if it would make it someday into a stamp, but anyway, it's quite a remarkable technique. With that, I would like to thank you, all the collaborators in the University of Cambridge, with whom I started developing this research line. Also, Professor Smith-Mende in Constance and Professor Wan in Texas, and funding from these other different bodies. And of course, all of you for your kind attention. Thank you very much. Do you have any questions?
Thank you, David. Excellent presentation.
Thank you.
Very elegant way of preparing these near-perfect films.
Thank you.
Questions for the speaker? Yes, please.
Thanks for your presentation.
You're welcome.
Can you explain more about the coating of silver nanowires? What is the effect of this coating?
The effect of this coating, when you anneal the nanowires, or where the temperature, when you try to pass too much current, the temperature increases, and then you get the Rayleigh instability. and then they spheroidize, so you lose the electrical contact. So that your network is not conducting anymore. These transparent conducting materials rely on a percolating network that ensures that the current can flow from one electrode to the other. If you increase too much the temperature, they are going to spheroidize, and then your connection is lost. So you need to prevent that, either if you're using it as a TCM to make sure that they are stable, and even from the atmosphere, because we are using them. Silver is quite sensitive to sulfur. There's sulfur in the atmosphere, so if they are not passivated, they could react with sulfur, and we have observed that in some of our samples. And also they could spheroidize. So this oxide coating just prevents that, and the exact mechanism, we don't know it yet for sure. But it helps release the heat or prevents this spheroidization. That's something we are currently studying. For coating it, the ones in the image are zinc oxide deposited by Spatial ALD, and we had tried first while we were getting ready our Spatial ALD by conventional ALD. We deposited TiO2, and it also enhances the performance.
And how about changing the conductivity of the nanowires? Because they are metallic nanowires, and you are coating them with zinc oxide.
Yep.
Zinc oxide is not
Yep.
superconductive like
Yep.
nanowires. So
But you coat them once they have been deposited, where you have the contents on, so the electrical connection is already made. So you coat the network, not the nanowires.
oh, I see.
Yeah.
And did you heat the sample after coating?
Yep.
Do you have
I'm showing electrical annealing. I don't have it here. I can look for it. Probably have it, but I'm not in this presentation. But we also see an enhancement in. I should have put it indeed because it's quite remarkable. We can go to 300 degrees almost, and the network is still stable. So yeah, yeah. You're welcome.
Very interesting approach. I look forward to getting one here. I just have a question about what do you think have you looked into what the limits of thickness, like film thickness, when you're trying to coat a porous material? I imagine there must be some pretty strict limits in terms of how far these penetrate.
Yeah, I would say that this is one of the limitations in terms of speed for this technique. If we go, let me see, maybe, yeah, right, the good one. Here, of course, we have a flat surface that is in direct contact with the nanowires, with the gas flows. So you're going to saturate the surface very fast. You don't need to worry about this issue. On the other hand, if you go to this other case where the trenches are, I went too back. This one, sometimes it does. Here, of course, you have a really high aspect ratio feature like a Lumina template, then you cannot scan as fast. Or when you can come up with a design of your head maximizing the speed at which you can scan. But of course, you need to give enough time for the gas to reach the bottom, for the inner gas again to reach the bottom to clean the pore, and so on. So you can still make it. We haven't done it yet in a systematical way, but I'm sure that the speed with the current head as we have it will be not as high as you would do it with a flat surface. Yeah, definitely. Yeah.
Irene.
Sorry. Yeah.
So getting back to the zinc oxide passivation layer on the nanowires, so you said it's not that conductive, which is fine for a heater, but for a solar cell, the nanowires need to connect with the surface of the nanowires. Need to make an electrical connection with the
Yeah,
box.
of course.
Is there a way of
Of course, yeah. Of course, ideally, you should protect them if it's conductive, all the better, because you're going to have a contribution from the zinc oxide. But in this case, what is more important is the lateral conduction from the active material to the electrode. This is guaranteed by the nanowires. You just need enough tunneling current from the active material to the nanowire to allow the charge to be collected. So if you use a thin layer of oxide, you're going to manage. Of course, the thicker the layer, the more stable it is, but the thinner, the more tunnel you have. But for instance, for photovoltaic solar cells, you are not expected to heat your sample a lot or to have huge currents, so you shouldn't need a huge amount of protection because you won't get high currents or high temperature. It is more important for transparent heaters, for instance, and in this case, the thickness of the zinc oxide is not as important because there's nothing that has to go through.
Can you dope
Yes.
materials
Yeah, sure.
with this?
With yeah.
Can you dope the zinc oxide?
We haven't done it yet. Well, we haven't started doing it with aluminum. And when we were at Cambridge, we did it also with magnesium, with nitrogen. So yeah, you just need to add the bubbler with the dopant precursor, and it's quite straightforward. Not always, but yeah, can be done. Yeah.
Regarding your percolation network of silver nanowires, can you make that more efficient by sorting that systematically, or is it all based on random, how the wires end up?
That's a good question, and we're kind of studying it now. We're kind of studying by modeling whether it's more appropriate. I would say that traditionally it's been considered random is better because you ensure a collection from pretty much everywhere. But we're trying to model it to make sure that nanowires is the best nanostructure, and that the random orientation or random distribution is the best option. I still have my doubts, but as I say, I collaborate with Professor Bellet in this topic, and I do mostly the chemical part, the coating, and he's more into the physics, and he's more into this topic. And I had some discussions with him and his PhD students, and I consider that I think we could win a bit by trying to combine random with ordered. But we are in the process of discussing it, modeling it, and trying to see what works best. Yeah.
Right. Okay. Let me ask you about the copper oxide. You said you go from a carrier concentration from 10 to the 13 to 10 to the 16
Yeah.
by SALD.
Yep.
But you also said it gets more perfect. So you have, less disorder, fewer vacancies, but more carriers?
The one with 10 to the 13 is electrochemically deposited.
Right, so
It's not the same deposition method.
exactly.
And
So
I don't know the reason behind this higher carrier concentration. You haven't had the time to study it in detail.
yeah, because it sounds counterintuitive.
That you have higher carrier concentration.
Yeah, if the film is nicer.
Well, it's nice. It means that it's nicer mechanically
Yes.
and structurally, but where you have your I would say maybe you have some metallic copper that you cannot detect or vacancies that you cannot see in the high resolution TM.
Right, because
So-
normally I would say, the carrier
Yeah.
concentration is higher. You will
Yeah.
have more vacancies,
Yeah.
not less.
Yeah.
Okay. Yes.
As you know, there is one way to create nanowires from top-down method, getting to etching. for
Can
example.
you start again? I didn't
Okay,
hear.
one way to create the nanowires is top-down method.
Yep.
To etch the, for example, bulk semiconductor to create the nanowires. But the problem is passivation for this problem, for this kind of nanowires. Have you ever tried to passivate the nanowires, for example, gallium arsenide or gallium nitride, that they etched by, for example, dry etching?
No. We've never tried to coat such materials, but not as film of. You mean while they are growing or after grow?
No, after they etched, for example, the bulk semiconductor and they fabricate nanowires, so the active region is exposed to air,
Yeah.
and we have a lot of dangling bond on the corners,
Yeah.
sidewalls.
Yeah.
So we need a very good passivation layer.
Okay.
I'm wondering if you have used before your device
No.
process too.
No, not for this type of materials.
So the next question is, have you ever measured or characterized the optical properties of your layers?
Yeah, that's something.
Waveguide applications, for example.
Especially for the TCO applications, that's something that we do. Of course, This BH thesis is the objective is to deposit this aluminum doped zinc oxide as TCO for the silicon heterojunction solar cells. So of course we do the measurement of the optical properties in order to know the band gap and all the optical properties. Yeah.
To make it more transparent or no? Optical window or something like that.
But so far, it's not optimized. I think you should talk to Viet to have the details because he's the one actually doing it. But we get decent transparency films, and it's more a problem of conductivity right now than transparency.
Okay. Then let's thank the speaker again for a terrific
Thank you.
presentation. Thank you very much.